So let's do a full sketch, and let's start with an easy one. From advanced functions, you actually know how to sketch this without even, without even like doing any kind of analysis with calculus. You know this is a cube, like a degree 4. So if I factor x to the power of 3, you get x minus 8. You know it's going to look, with 8 here, 0. 0 will be a cubic function, a cubic root. So it's going to look like this. It's going to do that. That's going to be the general shape. You already know this. But we can be a little bit more detailed in terms of where exactly that happens. Where exactly that happens now. Okay, step 1 is to, using your basic knowledge from advanced function, analyze f at x. Meaning, this means 1a, end behavior. So what happens as it goes forward to the right and forward to the left? 1b, roots, x-intercepts, and y-intercepts. Okay, you need to get these information out of the function given ready. Okay, so for step 1a, for this particular example, it's this, right? When x is approaching negative infinity, it's y is approaching positive infinity. When x is approaching infinity, y is also approaching infinity, because it's degree 4. Roots, it's equal to 0 and 8, right, from this factor form. Y-intercept is going to be also 0. Right, so you pass through the origin. Step 2 is to analyze, the derivative function. So this is easier to differentiate. So I'm going to pick this one and differentiate that in the expanded form. So 4x cubed minus, I guess 3 times 8 x squared. Factor as much as you can. 4x squared, and you get x minus 6, right? So critical numbers are x is equal to 0 and 6. You do a quick first derivative analysis. So this is totally up to you. At this point, to determine if this is a local max or minimum, you can do first derivative test or second derivative test. So I know that this graph here is a cubic function, right? So it's a cubic function with 0 and 6. That looks like this. Okay, so look, because the sign does not change here, right? It's negative, negative. It's going down and going down. This is not a local max or minimum. This, though, it's going down and up. Down and up. It's a local minimum. Okay. In fact, even from the first derivative, you can see that because it's going down and down on the 0, you can sort of, feel that this is an inflection point. So you can make a little table, right? This is up to you. I don't like making this table, but I guess when you're a beginner, you can sort of make the table, and you put your critical numbers down, 0 and 6, and here you put the sign of the derivative function, which is going to be negative, negative, right? And then positive. So you know that's going down, down, up. To me, this graph is more than enough. Okay, but if you want to just clarify to yourself, that's what's happening. That's how you make the table. Last step, step 3. Actually, before we move on, it's actually a good idea to find the actual y value. So to this last row, let's find the y value. When you plug in 0 in here, you get 0. What do you get if you plug in 6 in here? You get 6 cubed times 2. It's quite large, so just keep that in mind. Step 3, analyze the second derivative. Okay, so from here, I'm going to differentiate one more time. You get 4 times 3x squared minus 3 times 8 times 2x. And you can factor out 4 times 3 times x, and you get x minus 4, I think. So let me just make a quick correction here. There was this should be a negative 432. Okay. So look, do you see what's happening here? Remember I said I knew how it looks approximately? This is going to be 6 and negative 432. Just for reference. But let's continue on with this detail analysis. From here, potential point of inflection, okay, potential is occurring at x equals 0 and at 4. Okay, let's make a table like above. The second derivative, all the numbers on the top, it's 0 and 4. So look, this is a parabola, right? So it's going to be negative in between and positive outside. Okay, so that means it's it's concaving up here. Right? It's concaving up, it's concaving down, and concaving up. So this is both inflection point. So we did our due diligence in the 3 functions, first derivative and second derivative. Now it's time to put it all together. Okay, in one box. So we're going to do that all in one box. Okay, so I can see all of it at once. So the top still represents just a number line. Okay, and you got to put all your critical numbers, meaning like the critical numbers as well as the potential point of inflection. Okay, so that's 0, 4, and 6, right? And then the first derivative, the second derivative, and our y value. Okay. So I have the separate charts, but I like to put it all together. Okay, so from here it's right 0 and 6. So here, from here, I'm just gonna copy the same thing down. 0 and 6. It was negative all here until after 6 it was positive. Okay. For the second derivative, it was equal to 0 at 0 and 4, and it was positive, negative, and then positive. Okay, look. Now we have to combine these two information. Okay. Look, it says it's going down, but it's concaving up. Going down, but it's concaving up. So its curvature must be like this. This is still going down, but it's concaving down, so it must be like this. Okay, and it's same. All oh, sorry. This is still 0, so that's an inflection point. And it's going down and going up again, so it's doing this, going down, but it's concaving up. And then it's going up, up, concaving up, going up, but concaving up. So it's a minimum. So we already found these values. This is minus 432. This was 0. And at 4, we got 256. Okay, great. So now we're ready to draw. Okay, we know approximately what it looks like. The end behavior is up here. Put down your x-intercept, y-intercept first. So it's 0 and 8. Right? Make sure you leave room for 4 and 6 as well, because those are the critical numbers. So clearly at 0, 0, it's an inflection point. So it's doing this. Okay. And at 4 and negative, so this I can't draw this to scale, obviously. So at 4 and negative 256. So let's just say around there is negative 256. So it's gonna go down. Well, and it's gonna change concavity there. And at 6, it's going to be going down to the minimum value of negative 432. and then it goes up all the way really sharply up to 8, like that. Okay. So we have a similar picture as what we learned in advanced functions, like this one, right? But it's a lot more detailed, where we know everything to a lot more detail.